So you could understand that what I'm saying now is a way of understanding solution rather than.
Well, I totally believe in the mission.
Yeah.
So I just want to understand what this means.
So the first statement is that, did you know that the Anderson insulator is a gapless insulator? Yeah, okay. So it has a continuous spectrum. It's not like a band insulator or a Mott insulator or something. It's gapless. The reason why it's nevertheless, I mean, normally you think gapless systems are metals. The Anderson insulator is not a metal because the states near the chemical potential are localized. In fact, in 2D, all states are localized. So no matter where you put the chemical potential, they're localized. Okay? Okay. So I don't know. I mean, I'm going to make some plot. Don't take the shape seriously. So this is the density of states of the Anderson insulator. Okay, it's just some smooth function. Okay. Now, I know these eigenstates. Each of them has some wave function. Yeah, and that's what enters into the pairing of exact eigenstates. And I will not make any assumptions of homogeneity and so on. You should look at our paper. Okay. Now, suppose the chemical potential is somewhere. Right? Now you turn on attraction. That's the way this pairing of exact eigenstate works. So what happens? What happens is that let's not worry about whether there are pileups in the density of states or not and so on, but some gap opens up and I should center it around the chemical potential because that is the nature of pairing. Okay, so this is the pairing gap. This is, okay. Now, if you look at these states or these states, okay, if you now start asking for local gaps, then it turns out that these states are gapped because they are just away from the chemical potential, not because they're really gapped. So therefore, we see even larger gaps far from the chemical potential than we see. So this is where there is pairing amplitude, right? Because that is the piece which is affected by very inhomogeneous. Over here, and same here. With me? States in the Anderson insulator which are living here live at sites at which pairing doesn't affect them. Here also the states which are lying far from, let's put it even further, it's not affected. Yes? So what I'm saying is where there is pairing, you see a small gap which is from pairing. Where there is no pairing, you feel that there is a huge gap locally because you're very far from the chemical potential. If you look at that state, it's living very far from the chemical. So there's nothing at the chemical potential of that. See, tunneling density of states has a wave function squared times delta function summed over all n. With me? So that's one. Do you get some physical picture now?
I think so. And what I do not understand,
yeah.
So where is now actually, I don't know whether this question is well asked, but where is superconductivity happening? At the sites where there is air potential?
Yes. Of course, that is the definition of superconductivity.
I would think so. Okay.
This is the definition.
Yes.
Yes.
I sort of had the same question, so I'm starting from same point. So what you're saying is that gap can be everywhere, but you will get a pairing only if you have something to pair.
That's right. Because what happens is pairing involves some kind of particle hole mixing. Right? These are deep below the chemical potential. So they actually already have that's what I called that you can take out lots of distant valleys. So you can take out here, the gap will look like this. This is the chemical potential. A lot of spectral wave here and very little here. This is in a hill because it's at a high energy in the here. From the chemical potential, it will look like there'll be no spectral wave here, basically. But here there'll be
I think I don't quite understand what you mean by here. Is
okay.
Here,
So
the
point is what states lie low down in energy in an Anderson insulator? Those which are in deep valleys, very low energies. Yes. So you already have 2 electrons in there. You can't really make electron hole pairs there. What lie at very high energies in an Anderson insulator? States which are living high on top of hills. So they're empty. That's why the chemical potential is here.
Yes.
Beyond the chemical potential, you can have particle hole mixing and get pairing. The only thing is, this is all happening in a highly inhomogeneous way, which we would have never guessed unless we did the Boglia-Bordosian calculation.
Does it mean that in the areas where there's no superconductivity, that the gap is actually too large to form Cooper pairs?
In some sense, yeah. I mean, it's not a gap. It's just that those states have spectral rate which is well below or well above the chemical potential. Therefore, we call them a gap. What do we call gapless? That which lives near the chemical potential. Okay, it's not a phrase we use normally by saying, oh, this is the gap state. It's not a gap state. It's very far from the chemical potential. There's no weight near the chemical potential. Maybe there's some little bit. I mean, if you do numerics in highly disordered system, but that's why it looks like this.
So the states where there's no superconductivity, where you get from the numerics a large gap energy,
they are far from the chemical
part away, but they see a large gap energy, but there is not like a
it's not a gap in our usual sense of the word. It's just that there is no spectral weight when you try to tunnel into those sites. Because there is no wave function to tunnel into. That's what. So the word gap may be misleading, but that's the way we interpret STM data.
Yeah, thank you very much.
Okay, sure. So that's the intuitive picture. So this idea that somehow the pairing amplitude and the energy gap are closely tied, as they are in homogeneous superconductivity, this breaks down in a very dramatic way. Yeah.
Sorry. In this sense, can we call this like a local real space gap in a sense?
You want?
I
just think experimentally. You're an experimentalist or a theorist?
No, I'm a theorist.
Okay, but think experimentally. It'll help you.
Okay.
If you tunnel into this position in space, is there spectral weight there? Yes or no?
As far as I understand, two ingredients. First, the energy that we choose.
Yeah.
Then the local density of state.
Yes.
That those states that are far away.
Yes.
Will be hugely localized.
Yes.
And most likely we never get a real tunneling. And
you can, but you have to give a large bias on the negative side. You can pull stuff out. Here you give a large bias on the positive side. You can put stuff in.
Okay.
Right? Because that's what tunneling density of states is.
Okay.
Spectral weight to add a particle on the positive bias side. Spectral weight to take out a particle on the negative bias. Okay. I may have got the sign wrong, but you know what I'm talking about.
Okay.
Because this negative sign of the electron always confuses you.
So gap here is in a sense of tunneling probability.
That's right. It's in the how much spectral weight do you have to tunnel in?
Okay.
Yes. That is the measurable quantity. Okay, maybe talking about it as a gap actually is hurtful, but it is what it is, you know.
So maybe a fair formulation to basically say, if we do tunnel spectroscopy, we are always probing the lowest energy single particle excitation.
It's not lowest energy. By changing the bias at that location, you can probe all kinds of energy.
No. In case we are talking about this gap.
Yeah, then near zero bias.
No, not about the superconducting gap, but just about that. Let's call it increase in the density of states that we are probing. So we are just probing the lowest lying single particle excitation.
So if your bias is close to zero, then you're probing things at the chemical potential. That's the way it works.
And we basically do not discriminate between like single particle excitations of, I don't know, some fermions or Bogoliubov.
No, so from your tip, you always tunnel real electrons in or out.
Yeah.
And then how they convert into Bogoliubov excitations is related to the matrix elements that enter into the definitions.
I have a question about the coherence piece.
Yeah, so actually, she was also asking me that it's a very bad name, which is stuck. There's nothing I can do to change that. Okay, but there is no coherence involved in the coherence peak. So let me explain why. If this is true, forget all this stuff. Just do BCS theory, income level. Then, if you calculate the density of states, then in fact, the coherence factors, which are UK squared and VK squared, which you all know, just never enter into the expression for the tunneling density of states. They cancel out. Okay, so then you can ask, what are these peaks and what is their origin? And the answer is extremely simple physically. It has to do with the fact that in BCS theory, so the coherence factors actually tell you how this is dying. Everyone with me, or do you want me to write down an equation? You can call it epsilon k or whatever, or k, doesn't matter. Everyone okay with the statement?
I actually don't think that I get you.
Okay, so what is the BCS spectrum? Now I'm not doing any fancy something. I'm doing textbook BCS theory.
What is epsilon k?
Epsilon k is, as always, the normal state dispersion.
Yeah. Okay.
The mu is the chemical potential. So let me plot this. So these are the two parabolas that I've drawn. You don't even have to draw the UK squared and VK squared and so on. I mean, we can write down what the spectral function. You guys know what the spectral function is? One particle spectral function, which is what, say, photo emission would measure. Okay, so that's given by, probably I'll get my U's and V's wrong, but okay, forgive me. Maybe Andre can correct me if I got my U's and V's wrong. Anyway, this is it's that. Okay, and what is the density of states? It's some normalization, some over volume, some over KAFP come, because in density of states you don't care which K states you go. Okay, so right now I'm just plotting this. So I'm plotting these parabolas, or if you wish, forget the U's and V's or keep them, I don't care. But they are just this hyperbolas. Sorry, these are hyperbolas because see, it's going to epsilon k minus mu. That's why it's linear. But over here comes the gap. This is one piece of the gap. Yes, now everyone is with me as to what I've drawn. Okay, so now if you calculate the density of states, so let me draw it this way. Since I have energy going up, let me draw n of e. So it's sideways, okay? Because I want to. So of course there are no states here. So the density of states at zero temperature is 0. Okay. If I go very far to positive and negative energies, you don't see the gap. You just see the original band structure. Well, that's just some constant density of states. Now, what happens near the gap? That's where the quote-unquote coherence peaks happen. Okay. There's no coherence. Actually, if you do this calculation, all UKs, VKs disappear. It's like a Van Hove singularity in this dispersion. That at this value of K, there are many energy states. The band becomes, the Bogoliubov band becomes very flat. And that leads to the 1 over square root singularity. Here and here. Okay. That's what it is.
Is it really a Van Hove?
Many states correspond to that energy because you've made a flat dispersion there. So it's a Van Hove singularity. But if I say that, people will kill me because the word coherence peak is just embedded in everyone's consciousness. So they call it the coherence peak. That's it. It is what it is. Yeah.
Yeah, so like this is what we get in the textbooks about the standard BCS theory and the density of states.
Yeah.
So historically, what was the reason for calling it coherence peaks?
I don't know. I think I don't know who first called it that and why. But okay, we are not going to be able to change that. So in my talks, I say coherence peaks in quotes, but okay. But it is what it is.
There's a question.
Yes.
I don't understand why it's Van Hove. What shouldn't a Van Hove should be like saddle?
No. So Van Hove's okay. Van Hove just says, look at where the velocity becomes small, you'll get a singularity. Just look up even Ashcroft moment. That's what's happening. In some sense, the K becomes 0 at that point. Do you see what I'm saying?
Yeah, but you take a parabolic band, for example, it looks like this, but it's not a P band. If you look at STM data, at least it's not.
No, if you look at STM data for a superconductor, of a garden variety superconductor, you absolutely see this.
If you look at radiography.
Which Bernal or twisted? Huh?
Bernal, you have parabolic band and you have a.
But do you have superconductivity in Bernal?
No, I'm not talking about superconductivity.
Yeah.
I'm just talking about bands.
Yeah.
And you look at the density of state.
Yeah, but that's a very different story. This is a that's a very different story. As you know, the band edge singularity in some band, okay, has a characteristic thing. If you have a parabolic dispersion in one dimension, you actually get a 1 over square root P. If you have a parabolic dispersion in 2 dimensions, you get a jump discontinuity. If you have a parabolic dispersion in 3 dimensions, you get a square root E discontinuity. But then you can just work that out. It's just algebra.
Yeah, I guess I confused the 2D versus 3D.
It's just that the dispersion is showing something, and that's why it's happening. You have a lot of states there. You just have to do the algebra.
Experimentally, when you're working with disordered superconductors,
Yes.
these coherence peaks tend to disappear.
So now you can ask another question. In many systems, either the coherence peaks are extremely weak or they disappear. I mean, you can look at twisted biogeography data. Even in the superconducting state, many samples don't show particularly interesting coherence peaks. Or if you look at cube plates, superconducting states have sort of coherent peak, but as you eat about TC, pseudogap remains and tunneling, that's so coherent peaks are gone. Now you can ask a different set of questions. Why do these pileups in the density of states go away? Right? That's the question you're asking. Why is it that many samples, many situations, you don't see sharp pileups?
One question, or another way of saying it is this a signature of something happening close to the transition itself, or not at all?
So actually, this is, if you see very sharp coherence peaks, and now I'm calling them coherence peaks, if you see very sharp pileups of the density of states, it is a very definite signature of sharp quasi-particle excitations. But there are many situations in which you may not have sharp quasi-particle excitations because, so let's come back to this situation. Okay, so there's too much going on in this picture. But what do I mean by sharp quasi-particle? There are delta functions in the spectral functions. Okay, but in many situations, you don't have delta functions in the spectral function. Okay, we know that from angle resolved photo emission in the cuprates and so on. What happens is that actually this can become very broad. Now the question is how broad? What is the line with broadening? Because the broadening in energy of this line tells you the lifetime, right? The longer they live, the sharper speed is. This will just destroy the speed. So tunneling people put this as what they call the TIDES parameter. Every time they have an E, they will say E plus I gamma. Where does the gamma come from? It came from something, disorder, inelastic scattering, something which we don't have too much knowledge of, but which is broadening my spectral function. As soon as you broaden the spectral function, all this shape changes dramatically. You know, this will, even at zero temperature, very low temperatures, this will like give you something like, and if you make it very broad, then it will look really different. In some cases, we understand where this comes from in detail. In most cases, we don't.
Mohit, how this TIDES parameter, because we know from Anderson theorem that it cannot be due to elastic.
That is exactly what I'm saying.
Yes.
Then they'll say there's some inelastic scattering or there's some inhomogeneity, so there's a distribution of gaps. We don't know where it comes from. It's just a phenomenological broadening parameter that experimentalists use to fit the data. Okay, in most cases,
In some sense, you remember in definition of quasi-particle, it's the lifetime must be much larger than the universality.
Exactly. But it may not be true somewhere. I mean, like for instance, in cuprates, we know that when you go about TC in photo emission, you just do not have any sharp quasi-particles, yes, either in the strange metal phase or in this underdoped pseudo-gap regime. Okay, now we can debate ad nauseam where that is coming from, but it's an experimental fact.
In cuprates, is the lack of coherence peaks related to that it's not a fully capped Fermi surface?
No. No. And in cuprates also something very interesting happens, by the way. When you pass through TC in the angle resolved photo emission and also corroborated by various transports such as thermal Hall or microwave absorption, you get very sharp quasi-particles. Okay. In fact, from microwave absorption and thermal Hall, it's known that the mean free path for nodal quasi-particles in YBCO at very low temperatures is a micron. So something dramatic happens when you cool through TC.
Yeah, here I can add something that is an experimental results we had seen is that in some superconductors, there can be rectification effects due to quasi-particles. And this is still not very well understood as far as I know. But in DOR superconductors like BISCO and YBCO, we find that this quasi-particle signature extends way down towards zero temperature.
This I don't.
And
so I don't know, Claire, if I answered your question. I sort of meandered a bit, but
This might be a very stupid question, but if
those are the hardest, by the way, to answer. Anyone who prefaces it, you cringe, saying, "Oh no."
if we have a real superconductor, and then there are some of them that do not have particularly sharp coherence peaks. And if this corresponds to a broadening in the band,
yeah,
this corresponds to a finite lifetime of something.
Yes.
Does this mean that an average Cooper pair has a finite lifetime? Or is this is this a weird thing to ask and it's not a sensible way to trace it?
No, because you're just adding this by hand. It could, I think it's a fair statement to say that if you're in the superconducting state, a Cooper pair lives forever. Okay, I don't think it's the lifetime of a Cooper pair. Maybe if you're just about TC and talking about the sort of fluctuation physics that Andre Lama was talking about, then there you can talk about lifetime of Cooper pairs and so on. But the lifetime of Cooper pairs is infinity. But somehow it's the Bogoliubov excitations. The question is how much of that is in. So now, so get superconductivity for a second. You can ask, what is this object for a normal metal? And the answer is in band theory, it's just a delta. So let's take a normal metal. So in band theory, so ignoring all electron and actually even electron phonon, just doing I'm measuring epsilon k with respect to mu, so just not to clutter up my formula. It's just that. It just knows about the band. Okay, but now what if you include interactions? So if you include interactions, we know how to do that within Landau Fermi liquid theory. Right? And then this object is the following. This is non-interacting. That's less we can put a 0. Okay, maybe this also gets denormalized because effective masses change and so on, but let's not worry about some other stars. It's not important. But now, so the pole still exists. But then I should be technically much more correct and say I'm looking K close to KF, I'm looking omega close to the chemical potential, but let's assume I'm doing that. Okay. But this can't be the full story because there's a rigorous sum rule that this integral must be 1. This you cannot violate. Okay, so what does that mean? Because this guy is the probability density of creating electronic excitation in the most complicated problem, translation invariant because I have K in the world. At a given K, summed over all omega, you must create it somewhere. It's like a probability density. Okay, so this is of course satisfied here. It's not satisfied here because I'm telling you that Zk is strictly less than 1, and it could be 1, but then it would be a Fermi gas, but it has to be strictly greater than 0. Landau Fermi liquid, but then the weight is Z, which is not. So there must be some incoherent piece. Okay. So instead of the spectral function looking like a delta function with, so I'm plotting A, K, omega for K fixed as a function of omega, it's a vastly, it could be like heavy fermion materials, Z could be a number of order 10 to the minus 3. Okay, so it can be vastly reduced Z. And then there is stuff. And the stuff can exist. Actually, more. Okay, and it's all of this stuff must take up the weight of 1 minus Z to satisfy the sum rule. So what I'm saying is, if you come close enough to the Fermi surface in Fermi liquid theory, you must have a pole. Now, if the residue at that pole is very small, maybe it's hard to see in an experiment, and everything looks incomplete. If 99% of it is in this, then it will not look unless you can do really sharp experiments. So at least in cuprates, it's known that when you're above TC, to the best of anyone's ability to measure things, there is no pole, there is no Z. It's broad as hell. But when you go below the superconducting transition, and mostly studied in BISCO, because that's where RPES exists, you suddenly see a sharp peak and other stuff. And you can do that in a K-resolve. So
it means that the superconducting condensate can be in some cases described by Golubov fermions.
So the interesting thing about Landau Fermi liquid theory is that, see, naive BCS theory is pairing real electrons. But if you really push someone, they'll say that actually we are dealing with the Landau quasi-particles. And so long as they exist, they govern all the important low energy physics of the problem. This is sort of very subtle and intricate point, which is usually not emphasized, but it's simply true. No, that's not what you were asking.
What I wanted to say is that in some cases there is a description of the condensate by a Golubov fermion.
No, wait, sorry. The condensate consists of pairs.
Yes.
The excitations are called Bogoliubov quasi-particles. Usually you don't use the word Bogoliubov with the condensate in superconducting.
Maybe what okay, then this, but
so this,
yeah, okay, this makes sense, of course. Yeah,
this object is the spectrum of the Bogoliubov quasi-particles.
Okay, then I think this is much more clear. Thank you very much.
Okay, sure.
Questions? You all posted?
I mean, I'm around. It's not as if you haven't asked me a question. You can never ask me a question. Don't worry. If you're tired, you can all go home, enjoy the sun, eat.
I do have one question, which is about the very beginning of your talk of this afternoon, and I'm afraid maybe there is something I misunderstood. So it was when there is this very first model, when you have this V of R, this like random space potential.
Yes.
And then when you show the results of your model and you put side by side this V of R and then I guess it was the energy gap over space, you showed that the grains seem to appear in a way which is their spatial appearance seems to be completely decorrelated from this spatial way of ordering it.
Okay, so you are right. That's the image that you get. But of course, if there was no randomness, no granularity would have emerged. So it is this random potential that's giving rise to the emergent granularity in the pairing amplitude. But the relationship between the two seems very subtle and unclear to the eye.
Because my question is, like, what are you modeling when you decide to use this V of R? Is it like, I don't know,
disorder?
Disorder.
Yeah, because suppose I had no interaction whatsoever, no superconductivity. Go back and look at Anderson's paper on Anderson localization. It solves precisely this problem. Electrons hopping on a lattice in a random potential which is uncorrelated, independent random variables at each site. So it's disorder, which is just impurities.
Because what I feel is like, if you have a sample, you expect your superconductivity to be like better where there are no impurities, and then weaker at.
So you could use the following model, which we have not. But instead of having V of R as an independent random variable at each point, which takes on values between minus V and V, okay? You could have said that with probability P, you put a scatterer. And with probability 1 minus P, you don't put any scatterers. It's like some kind of binary disorder. We haven't done that. But from whatever we know about Anderson, it would be probably worth thinking through that. But from whatever we know about Anderson localization, yes. I mean, some details may change, but it doesn't matter how you model the disorder in detail. The phenomena of localization still persists, but this can be done. And perhaps you're saying that may be a more realistic view.
Yeah, I don't know. Yeah.
no, the thing is, okay, we thought about doing that in the early days. And then we thought that, okay, when we have very dilute impurities, which is low disorder, it may seem something happens where there are no impurities. And we didn't want that, you know. We wanted to say, okay, let them be everywhere and fluctuating, maybe fluctuating a little less. That's the low disorder, and fluctuating a lot more, high disorder. Let's see what happens. We are not biasing the system into saying, make a puddle here or do this there. Yeah, so that was a theoretical reason, which may not be the most realistic description of disorder in an actual material. Okay. Yeah. Okay.
Okay, you'll get a second chance of asking anything you ever wanted to ask.
Yeah.
To those two guys tomorrow. So,
you had another question?
sorry.
Yeah, I was wondering why it's still random, because okay, potential from impurities should probably have quite determined look. Probably it's Coulomb potential, or
so if you start putting Coulomb potentials and so on, it's very hard to do even the Anderson localization problem, let alone this interaction versus localization problem. So as I said earlier, as theorists, we do simplest. If it comes out totally irrelevant to the experiment, then we have to go back to the drawing board.
I would maybe like to comment on that. So you say that why is the potentially random, whereas purity should be like repetitive. Imagine, look at so I know only about my material, and we have like a bouquet of different impurities. So we have oxygen, we have nitrogen vacancies, we have leftovers of the precursor, which is a large molecule which can be left in different sizes. We have lattice mismatches, and then already you have like 5 things that look differently at random locations. So I don't think that I think that's a pretty good idea. Let's say put random potential and that models us pretty well, and the results fit the results from my material experiment surprisingly well. It's very, very nice.
I'm sure details can differ. I mean, I'm not denying that, but I think, yeah.